remember the square root of x plus 1? We always have to write that x plus 1 is greater than or equal to 0. Remember 1 over x minus 3? We always have to write that x cannot be 3. The square root is not a friendly function because the quantity under the square root has to be greater than or equal to 0. The rational functions, for the most part, are not friendly functions because the denominator cannot be 0. Now, this is the next or the last function that has problems or potential problems. Log. Log has to be applied to positive numbers only. So in this case, I have to write that x plus 4 is strictly greater than 0. That's how I find the domain. Log can be applied only to numbers strictly greater than 0. So once I write that x plus 4 is greater than 0 and x is greater than -4, the domain will be -4 to infinity. That's all we need to do. So please remember, this is a review and a summary of the functions that we encountered with problems. Nothing else has problems. Logarithmic, a polynomial, absolute value, exponential, all friendly. These three we always have to be careful with. Okay, so now let's choose anything else you'd like to work on to determine the domain. So let's choose.
Can we do 80?
Yes, please. So in 80, we have f of x equals natural log of x minus 7 squared. Perfect. So the only situation, the only condition that I have to, or restriction that I have to write is x minus 7 squared is greater than 0. But you can say, but this is always positive. Why do we even write that? Well, that is true. This is always positive. But there is one number that has to be excluded because it will equal 0. So this is indeed always positive. But however, this quantity can be 0, and that cannot happen. So the domain will be everything except that number that makes this expression 0. So what is that number that has to be excluded?
Would it be 7?
Indeed. See, any other number will be positive, so it's safe. But 7 minus 7 is 0, but 0 is not strictly greater than 0. So therefore, the domain for this function, or of this function, oh, I forgot to number my, that was 12, sorry, 13 and 14. Okay, so then the domain of this function is, in plain English, everything except 7. Very good pick. Anything but 7. Good. Let's look at anything else. What will you say for 79? Anything but?
2.
Indeed. Okay, let's choose one more. Can we do 77 or 78?
78.
Okay. In 78, we have f of x equals common log, because it's base 10. If the base is missing, it's common log. If it is ln, I know it's base e. So the same question, we are asked to find the domain of this function. What do I have to write and solve in order to find the domain? Can anyone tell us what to write? What do I have to write and then solve to find the domain?
Okay.
Yes, Christy, what should I write?
Would it be x restriction of 7?
So 7 minus x must be so then 7
0.
indeed. That's it. And now I have to move 7 to the other side. I have to multiply or divide by -1. What do I need to do every time I multiply or divide both sides of an inequality by a negative number? What do I have to do?
Flip the
Yes, from greater than to less than. So now the domain for this function is from -infinity to 7. Good. I'd like to look at a word problem to see the multitude, the vast multitude of applications of log and exponential. So this is a log. Students in a psychology class took a final examination. As part of an experiment to see how much of the course content they remembered over time, they took equivalent forms of the exam in monthly intervals thereafter. The average score for the group f of t, that's the average score. So let me copy the function. So this is 119 on page 493. So f of t equals 88 minus 15 times natural log of t plus 1. And t is a number between 0 and 12 months. The average score for the group f of t after t months was modeled by this function. What was the average score on the original exam? Original or initial? What am I asked to find? So this is the score. And t is in months. So what am I asked to find? So I'm asked, find the original score. What does it mean? What am I really asked to find when they say find the original?
Would it be the score?
At when? What time? The original.
Would it be 0?
Indeed. That's what it means. Original or initial or starting point. That's the starting point. We're going to determine it in a minute. Part B. What was the average score after 2, 4, 6, 8, 10, and 12? So 2, 4, 6, 8, 10, and 12. Good. So I'm going to create a table so we can see what's going on here. So here's t. So here's f of t. And we have 0, 2, 4, 6, 8, 10, and 12. Good. Graphing calculator. Put the function in. It's the best way. Do not try to repeat the process 10 million times. There is no need for that, something like that. Enter the function minus natural log. No. Minus 15 natural log of t plus 1, close the parentheses, check the function, correct, second and table, and put those quickly. 0, enter, 2, enter, 4, 6, 8, 10, and 12. That's it. Good. So the original score was 88. The next one is 71.5. The next one is 63.9. The next one is 58.8. The next one is 55, 52, and finally 50, or 49.5. That's it. That's the best way. Don't repeat the process and enter it 10 times. Create the function in the graphing calculator, put the values, and get the y values immediately. Enter the x values and determine the y values ASAP. Good. Back to the problem. Sketch the graph either by hand or with the graphing utility. Describe what the graph indicates in terms of the material retained. It's very clear what it indicates. What does it indicate?
It is decreasing.
Indeed, absolutely. Thank you. So let's take a look. I already have the function in the graphing calculator. I put it in. Now the standard viewing window is not going to work. Okay, it starts at 88 and it drops to 49. So the values are from 88 to 49 and the x values from 0 to 12. So careful, because I have to adjust the viewing window in order to see the graph. So I'll go directly to the viewing window, and x minimum is 0. X maximum is 12, for sure, with a scale of 2. Now the y minimum is roughly 50, right? Because the minimum after 12 months is roughly 50. So I'm going to say y minimum 40. And y maximum is definitely above 88. So I'm going to put 90. And with a scale of 20. Here it is. If you use the standard viewing window, you're not going to see anything. Nothing. Because 88 is at the top and the minimum is 50. And this is 0 to 10. So we have to adjust the viewing window so we can see what we need to see. And that is 0 to 12 with a scale of 2. And the minimum 40. Maximum 90 with a scale of 20. I don't need those ticks to be too many in the graph. And now I see. And here's the graph, starting at 88 and dropping 12 months later at roughly 50, 49.5. So there are many, 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 many applications that involve either exponential or log functions. So here's another one. So the percentage of adult height attained by a girl who is X years old can be modeled by this. Look, another log function. This one had natural log and this one has common log. X represents the age from 5 to 15 and f of x represents the percentage of her adult height. Use the function to solve these two exercises. Approximately what percentage, which is f of x, of her adult height has a girl attained at age 13? So since x is 13, all we have to do is enter this function in the graphing calculator. I'm going to write it here. So this is f of x, and this is problem 113 on page, what was the page? 493. So let me enter the function. 62 plus 35, common log of x minus 4, and we're asked to enter 13. And we're going to enter 10 later on. So again, the best thing to do is enter the function. Make sure you enter it correctly. You can take a look at it and make adjustments if there is a mistake. And it's common log, and this is x minus 4. And you have it there. You can graph it also, and you can plug in more than one value. So they're asking us to plug in 13, and I think the next one was 10. So here's the percentage. 93%, 89%. So for 13, the attained height is 95% of the adult height, and at 10 is 89% of the adult height. And look at the function. It involves a common log. Any questions? Any questions? So let's summarize a little bit, because it was a lot of information. We went as slowly as we could, but it's still a lot of information. So let me summarize a little bit. So we're looking now at two totally new functions, but these two functions have a lot of applications in real life situations. The exponential and the log. They're inverses of each other, and we prove that with a very important topic in which we said any log function can be changed into an exponential, any exponential can be changed into a log. So we showed how these two work. So we looked at the exponential function and the base for both. The base can be greater than 1 or tiny, positive. So the base will never be 0, 1, or a negative number for either one of them. Then we graph them. We graph the exponential function with the base greater than 1, and then the log, the inverse function. And we went through all these properties. Increasing, domain and range, horizontal asymptote, the fact that it's 1 to 1, so it has an inverse. And then this function we realized is a function with restrictions, because it can only be defined, it is always defined on positive numbers, as you see from 0 to infinity. Okay, and then we looked at these two special functions, exponential and also log, common and normal. Then we graph the other exponential function with a base less than 1, and we realize that it's a decreasing function. So is its log function. Okay, then we use some transformations. We reviewed the transformations on exponential functions. And we just learned how to graph an exponential function, but we were able to go through these transformations together. Then we look at the formula that has exponential and compound interest n times per year and continuously. So this is another a base raised to a power. So that's why they're both here. Base raised to a power, base raised to a power. Accumulated value, principal, annual interest rate, time in years, and E is Euler's number. He was a Swiss mathematician. Okay, and we looked at some problems in which we plugged in. So here was a word problem about percentage of retaining what we retain, the information we retain, number of weeks. The table always is a very good picture and a visual representation. Then the most important element here in this chapter, any log equation can be converted into an exponential, any exponential can be converted into a log. For that, we proved that indeed 2 to the x and log base 2 of x are indeed inverses of each other. This applied to -3 gives this. This applied to 1/8 gives this. And then we practiced, and then we looked at the log. We identified pairs of inverse functions, and they must have the same, exact same base, otherwise they will never be inverses of each other. And then we simplified logs. We simplified more, and then we looked at these properties. These are properties that no other function has. Log of a product is a sum of logs and backwards. Log of a ratio is the difference of logs and backwards. Log applied to a power, I put the power in front. And if I have a power in front, where is it coming from? From the power of x. So again, back and forth. And the change of base formula. So then we simplified some more, and we simplified some more, and then we looked at the domain. Keep in mind that these three functions are problematic. They may have issues. This one, and now the third one. I promise you this is the last function of the semester. Please remember these three have potential issues. So we looked at the domain, and then we looked at another word problem that now involves natural log. We created a table. We graphed it with the graphing calculator. So again, this one was another function that had logarithm, common log, and we were asked to evaluate it. And that was